In this lesson, we're going to go over 4.1 to 4.3 and 4.5. That's mainly going to be looking at the relationship between f and f prime, digging into things like how do we justify mins and maxes on the graph of f by looking at f prime, how do we know increasing and decreasing regions of f looking at f prime, how do we know the concavity of f looking at f double prime, taking a look quickly at the mean value theorem, and also talking about L'Hopital's rule. So let's get into things. Let's start with this question here. Assume that I tell you that f of 2 is 10, f prime of 2 is 0, and f double prime of 2 is 5. Which of the following can we conclude? And the multiple choice options are, is it a local minimum, a local maximum, an inflection point, or a potential max or min, but you can't conclude which one. So let's take a look here and see. So we know f of 2 is positive. We know f prime of 2 is 0, right? So we know it flattens out at 2. So at 2, we're at 10. So say we're up here. F prime of 2 is 0, so we know it flattens out. And we know f double prime of 2 is 5. So we know that this is positive. And because it's positive, f double prime is greater than 0 means that f is concave up at x equals 2. So that function is happy there. We know that x equals 2 must be a local min given this information. So our answer would be local minimum. Using your calculus knowledge, what is a good way to justify that x equals 2 is a local minimum? So some things you could say, we know that f prime flattens out here. If it's a local min, then it would be concave up there, meaning f double prime of 2 is greater than 0. So, sorry, I forgot to specify at 2, right? The derivative flattens out at x equals 2, and f is concave up at x equals 2, aka f double prime is greater than 0. The other way to do it for local min, f prime changes from negative to positive at x equals 2. Both of those ways would justify. Now, in order to use the mean value theorem, we must determine that the function is both continuous and differentiable, because the mean value theorem is telling us that the slope equals the derivative somewhere. So we need to be looking at both the function itself and its derivative, that it's continuous and differentiable. Why must we actually have this? Well, this was an example that you did in your mean value theorem assignment, and I just want to showcase it here. So basically, you know f of 1 and f of 7 equals 2 in this case. So that would say that the slope between those two endpoints is 0, right? By the mean value theorem, the slope has to be equal to the derivative somewhere. And so that would mean that somewhere in the interval between 1 and 7, that f prime must also equal 0. But that's not the case. This problem, we clearly have that the slope is equal to 0, but we don't necessarily have that f prime of c equals 0. In fact, there's nowhere on the interval where the derivative equals 0 because the derivative does not exist there. There's a corner or a cusp. However, we could never even use the mean value theorem in the first place in this one because the function wasn't differentiable. So we could only apply the mean value theorem when the function is continuous and differentiable. So you need to state that before you ever start using the mean value theorem. Let's go ahead and try this problem. Let f of x equal 1 over x. Find all values of c, if any, that satisfy the conclusion of the mean value theorem on the interval negative 1 to 1. Well, f is not defined at x equals 0, therefore we cannot use the mean value theorem because f is not continuous on negative 1 to 1. Now, if they had given me this problem and the interval was instead 2 to 5, then I could have done it because this function here is continuous on 2 to 5, okay? So that's just a little subtlety. So I just have to look on this interval, is it continuous and differentiable? And if it's not, then I can't use the mean value theorem. Now, this one's clearly continuous and differentiable everywhere, right? So we can use the mean value theorem. So let's go ahead and do it. So mean value theorem, let's look at the slope first. So f of 2 is 4, f of negative 2 is also 4, all over 2 plus 2, that is going to be 0. Therefore, because our function is continuous and differentiable on the interval actually everywhere, and the slope between the endpoints, we can conclude there must be a c within our interval such that the derivative actually equals the slope, that the derivative actually equals 0. Okay, mean value theorem, the slope equals the derivative somewhere. In this question, this function is continuous and differentiable everywhere, so we can use the mean value theorem. Just going to go ahead and state it at the beginning. So now let's find f prime of x. 3x squared plus 6x, right? The derivative of 2 is 0. And let's find the slope. F of 1 minus f of negative 2 all over 1 minus a negative 2. F of 1 is 1 plus 3 plus 2. F of negative 2 is also 6 all over 3, which is 0. So mean value theorem, the slope equals the derivative somewhere. So let's find that c. So f prime of x, 3x squared plus 6x equals 0. We can factor out a 3x. We get x plus 2 equals 0. X equals 0. X equals negative 2. Now, we have to look. Are they within our interval? Can't be at the edge of the interval. Must be strictly within the interval. And I'm going to show you on the next slide why. We considered x equals negative 2, but it's not within our interval. So we have to eliminate that answer. We must show it and then eliminate it. So the only answer that we get is c equals 0. Let me show it to you graphically. Right here, this is our interval. So the slope between those endpoints is 0. We know the slope equals a derivative somewhere. Where does that happen? Well, that happens here, right? Here, the derivative is also 0. We had found on our last slide, c equals 0. If you looked at the whole graph, so if we didn't just cut off the interval, we would have seen that it zeroed out at both negative 2, right? And at 0. So that was why we had gotten both of these answers, right? But we had to eliminate the negative 2 because it was on the end. And that's why when we're doing the mean value theorem, it's strictly a number within the interval. It can't be on the end point, okay? Moving right along, in order to use the intermediate value theorem, well, the intermediate value theorem is just the one where like we can show a 0 by showing that we have a point for which that value is above 0 and we have another point for which that value is below 0. So there must be some c in between those two numbers such that we actually cross 0 if the function is continuous, because we're only looking at the function. We're talking about function values here. We're not talking about anything about its derivative. We're just looking at the function value. So if one thing was above 0, one thing was below 0, then we know we must cross 0 somewhere in between if it's continuous, if we don't have any jumps, right? We don't need to look at the derivative. We're not asking anything about that. So IVT, continuous only. MVT must look for continuous and differentiable. Let's do an intermediate value theorem question since we haven't done one in a while. So let f be a continuous function, so we can use the intermediate value theorem. And we know f of negative 2 is 3, so that's above 0, and f of 1 is 6, so that's also above 0. So this is not finding a 0. But we do know that between negative 2 and 1, between those x values, negative 2 and 1, that we must go through some number between 3 and 6. 4 is between 3 and 6. So it looks like the answer is D here. We don't know that it's 0, and we know strictly between negative 2 and 1 that we must pass through some y value between 3 and 6. You see, the x value is between negative 2 and 1, and the y value must hit a y value between 3 and 6, which is D, our answer. So let's do an IVT problem. So I made this long slide type, so I just have to show you my answer here. So basically, put in f of negative 1, find the value. That was 8. Put in a 2, the other endpoint, find that value. It's negative 19. Since f is continuous, we can use the intermediate value theorem. And because we had one number below 0 and the other value above 0, there must be a c, there must be some x value between x equals negative 1 and x equals 2, such that its y value is 0. Oops, I forgot something important. By the intermediate value theorem. Don't forget that. Don't be silly like me. Don't forget to say because it's continuous. And why? By the intermediate value theorem, we know that that's true. So that's that. Now, where is f prime greater than 0? F prime is greater than 0 means that f is increasing. And this is the graph of f below. So where is f increasing? 0 on and negative infinity to whatever that value is. So that's where f prime is greater than 0, where f prime is increasing. Now, where's f double prime greater than 0? F double prime greater than 0 means that f is concave up. So I'm basically looking for where my function is happy. So it looks like the inflection point is around here, right? So it's happy from that point on. So where I've shaded is where f double prime is greater than 0, because that's where f is concave up. Place a dot on all the points where f prime equals 0. So f prime equals 0, it flattens out here. Boom, it flattens out here. And that's about it. F prime equals 0 at those 2 points. What is the relationship between f prime and f double prime? So let's start with the example. If f double prime is greater than 0, means f is concave up. F double prime is less than 0, means f is concave down. That's the relationship between f and f double prime. Now they want us to tell the relationship between f prime and f double prime. So let's go through this. F is concave up when f double prime is greater than 0. But what does that mean about f prime? We know that f increasing means that f prime is greater than 0. We know f decreasing means that f prime is less than 0. We can take that relationship down a notch too. So just put a prime on it. So f prime increasing would mean that f double prime is greater than 0. See, I just put a prime on everything. If f is increasing means f prime is greater than 0, then f prime increasing means that f double prime is greater than 0. Just take everything down a notch. So same relationship, f prime decreasing means that f double prime is less than 0. If you can manipulate like this, you can do everything in calculus, okay? So f double prime is greater than 0. F double prime is greater than 0 means what about f prime? It means f prime is increasing. Okay? And what does f concave up mean anyway? F concave up is a function like this, right? What's happening to the tangent lines? They are actually going from negative to positive, but they are actually increasing in value, right? The slope, maybe it was -5, then it became -2, then it became 0, then it became 2, then it became 5. The value of the slope is getting bigger. F prime is increasing. F is concave down when f double prime is less than 0. We knew that. And what does f double prime less than 0 mean? F double prime less than 0 means that f prime is decreasing. Okay, graphically, that's a concave down function. The slope, say it was positive, getting less positive, zeroing, getting negative. It is decreasing over time, the values of those slopes. In summary, the relationship between f prime, and f double prime, f increasing means that f prime is greater than 0, f decreasing means f prime less than 0, f concave up means f double prime is greater than 0, which means if the derivative is positive, the function is increasing, so that would mean f prime increasing. F concave down means that f double prime is less than 0. If its derivative is less than 0, then the function is decreasing, so f prime is decreasing. That kind of summarizes things quickly. Hopefully you can justify that all in your brain yourself. Is this function differentiable? To prove that it's differentiable, let's first show that it's continuous. To show continuity, we need 3 things. And our point here of potential problem is 1, right? We know this is continuous, we know this is continuous, but at 1, we change definition. So we need to look at 1, the limit from the left, the limit from the right, and f of 1. The limit from the left is going to use this left definition, so we just put in a 1. The right, we're going to use this definition, so 1 minus 2, -1. And f of 1, we would use the top definition, which is also -1. So all 3 are equal to each other. Therefore, f is continuous. Now, to find differentiability, let's first find the derivative. We need a piecewise function for this. Find the derivative of each part. The derivative of -x is just -1. The derivative of x minus 2 is 1. So is it differentiable? I hope you can see no, it's not, because the limit as x approaches 1 from the left of f prime of x, from the left it's -1, but from the right the derivative is +1. Therefore, f is not differentiable. Please, when you're doing differentiability, don't forget that you must first show continuity, because if it's not continuous, it can't possibly be differentiable, okay? Find all intervals where f is decreasing, given that this is y prime, so they're actually nice to us. So f is decreasing means that f prime is less than 0. So that derivative, where is it? Negative is what we want to know. So y prime equals x squared minus 8 over x. So we better put this with a common denominator. So to get from x squared over 1 to something over x, we need to multiply by another x. And then to get from the 8 over x to something over x, it's just, we do nothing. So we have x cubed minus 8 all over x. So where are our critical values? Y prime equals 0 or y prime does not exist. Don't forget to check both. Y prime equals 0 when x cubed minus 8 equals 0, x cubed equals 8, x equals 2, and it does not exist when x equals 0. Put those on our number line. I'm going to put an open circle at 0 because it doesn't exist there. If I put in a negative number, I would get a negative on the top over a negative on the bottom, which is positive. If I put in a number like 1, I would get a negative on the top over positive, so that's negative. And if I put in a big number, that's going to be positive over positive, which is positive. F is decreasing when f prime is less than 0, and that happens on 0 to 2. That's my answer. We can use L'Hopital's rule if and only if our limit is of the form 0 over 0 or infinity over infinity in this class. Okay, there's other forms that we can use L'Hopital's rule for, but for this class, if it's of the form 0 over 0 or infinity over infinity, that means when I plug in the number and I get 0 over 0 or I get infinity over infinity, then I can use L'Hopital's rule, which says I can take the derivative of the top over the derivative of the bottom. So can I use it in this problem? Let's see. If I put in a 2, I have 8 minus 4 times 2 is 8 over, what's on the bottom? 4 minus 4. I have 0 over 0. Therefore, we can use L'Hopital. We have the limit as x approaches 2, and now we take the derivative of the top, 3x squared minus 4 over 2x. Now put in the 2 again. We get 3 times 4 is 12 minus 4 over 2 times 2 is 4. 8 over 4 is 2. We can check our work with an old method of simplification. Let's just do that while we're at it. Let's factor out an x. Ooh, that one was actually easy, wasn't it? Maybe easier this way. The limit as x approaches 2, we just have an x left, is just 2. So that's that problem. Let's try this one. So this problem we really can't simplify. So this other problem we probably should have tried simplifying first because we would have gotten something easier. But this problem we really can't simplify. So let's hope that we can apply L'Hopital. 8 minus 5 over 4 minus 4. We can't, but we have a finite number over 0. So that's going to be does not exist. On the top, it's always going to be a positive number, but on the bottom, if we take a number really close to 2, but to the left of it, let's just take 1, we would get a negative. We're dividing by like a 0 negative, right? And that would be negative infinity, but from the right side, that would be positive. We would have 3 over 0 positive, and so that would take us to positive infinity. A graph would look like this. So we would go to negative infinity from the left and positive infinity from the right. You should be able to do that without a calculator in your head because the numerator, as x approaches 2, is positive. It is 3 all the time. But then a little bit to the left of 2, that answer would be negative, but a little bit to the right of 2, that answer would be positive, and therefore we have a switch in sign, and that's why it does not exist. Now, a limit as x approaches infinity problem. Remember, all you have to do is divide by the highest power of x in the denominator to do these types of problems. So that's easy peasy. The numerator is larger, so it goes off to infinity. One more problem, and that should have been a W. So let's try putting it in. We have the sine of negative 4 pi. What is the sine of negative 4 pi? This would be negative 2 pi one time around. Negative 4 pi would be one more time around, still in the same place. So that would be 0. And the denominator is clearly going to be 16 minus 16, which is 0. Therefore, we can use L'Hopital. So take the derivative of the top. That is going to be a chain rule. Pi w is our baby. So the derivative of sine is cosine. Leave the baby inside. Times the derivative of pi w. W is our variable. That's just going to be pi all over 2w. So now the cosine of negative 4 pi times pi all over 2 times negative 4. And so the cosine is going to be the x value there. So that's going to actually be 1. So I have pi times 1 over negative 8, which is negative pi over 8. And that's really it for this lesson. 3 more things. Just remember in Slack to always be reviewing any pinned comments that you see there. In Slack also, I encourage you to use the Zoom sessions channel that I've created in there. The reason that I encourage you to use that is if anybody else wants to join your chat when you're doing it, they could if you were posting it in there as opposed to if you're texting one another. And then the Trimester 1 project is something that we're going to be doing next week. So you'll be turning that in on Friday. So just make sure that you take a look at the guidelines, and I have a sample that you can view. So if you just look at my tutorial example, you'll understand that the purpose of this project is really to compare old stuff with new stuff. So you're going to take things that we did before. So say that we did these limit problems and we just had to work out all the messy algebra. Now we have different methods to solve this. We can use L'Hopital's rule. We can recognize it as the derivative definition. We have a lot of new knowledge to do a lot of these problems. So you're going to look back at things from chapter 2 and you're going to do them with our new knowledge as well. You have to do some flip grids in here. There are 10 artifacts that you have to have in here. You need to just read through this whole entire thing. You need to look through the tutorial, look through all the project details, and then I also give you a list of the topics we've done just as a reminder in case that's helpful to figure out what problems you want to do. There's an end of project checklist to make sure that you're doing everything you need to do, and then there's a rubric right here. Make sure that you are adding a flip grid. That's part of your assignment, and you can just add it to this flip grid that is embedded right here. So that's going to be your big project that is going to be worth an assessment grade. So it's going to be worth an entire quiz grade, and you should be able to get full credit if you do all the components. So read very carefully on what's due. As well, you have a pear deck that you have to complete. So you're going to be working on this pear deck. You're going to turn in the pear deck on Tuesday, and then you're going to do revisions to that pear deck. So that's going to be your only assignments next week. You're going to be working on that all week long. Okay, so that's it for me. Hope this helps.